Hello. In this segment, we'll try to understand some basic backgrounds of specific energy and then the specific energy curve. So, to memorize, we are in the non uniform flow case. The non uniform flow may be caused by the change in width, depth, bed slope, etc. of a channel, and it is also due to an obstruction constructed across a channel of uniform width. We also know that there are two basic types of non-uniform flow. The first one is gradually varied flow. We call it GBF. And we also have the second type, which is known as a rapidly varied flow. And these two types of flows are classified based on the change of depth of flow over a well-defined length. So we'll try to understand the total energy and the concept of specific energy first, and then we'll move on to the concept of specific energy curve. Now, the total energy of flow per unit weight of a liquid is given by the well-known Bernoulli's principal Bernoulli's equation. Total energy is Z plus Y plus V square by 2G, where Z is elevation of the channel bottom above the horizontal datum. This is Z, and Y is depth of flow, and V is the average velocity of flow. Now the same thing is exemplified in this diagram, whereas specific energy is the energy which is defined as the energy per unit weight of flowing liquid above the channel bottom. The very difference between total energy and the specific energy, which even you can identify here, is in specific energy there is a term called Z which is absent. A specific energy is the energy which is always measured with respect to the channel bottom, where Z is always equals to 0, and it is this specific energy where which forms a sum of potential energy and just a kinetic energy. So y plus q square by 2g y square, where q is the energy per unit width. So we all know that velocity is discharge per area, discharge by area for a rectangular cross section is b into y. You just substitute q by b is nothing but small q, and that's how E is equals to y plus q square divided by 2g y square. Now we move on to the concept of something called, which is very important, the specific energy curve. The plot of specific energy curve, it consists of the depth of flow in y-axis and specific energy in x-axis. It consists of varied variety of zones here. Now let us try to understand the concept of specific energy one by one. So we start with a basic equation. E is equals to y plus q square by 2gy square, or to sum up it is E is the specific energy is the summation of potential energy and kinetic energy, and all these explanations deal with a rectangular cross section where width is b and depth of flow is y. Now there are two components when it comes to the specific energy. You just refer to the same equation. First component is E equals to y, the second component is E equals to q square by 2gy square. Now it's very evident that if you plot E is equals to y, it becomes a straight line where the slope is equals to 1, or the angle which you can describe is equals to 45 degrees. Now this is EP is equals to y is the first part of this equation. The second part of the equation is the plot of depth of flow versus energy is EK. EP is potential energy, EK is the kinetic energy, and in kinetic energy you have 1 by y square. So obviously it's not a linear line. So the curve for kinetic energy is a parabola. Plot for specific energy is obtained by adding kinetic energy to potential energy. So the resultant curve which we are supposed to analyze is the resultant one, and the resultant curve is this. So this is the resultant curve. EP equals to y, ek equals to q square by 2gy square are the individual curves, and the resultant curve is this. And at certain depth yc, the speciality of this resultant curve is that at certain depth yc, and this yc is called critical depth, which is denoted in y-axis, the specific energy curve has a point of minimum specific energy. The corresponding flow velocity is called the critical velocity v. Uh, there are three things associated with the point C. The point C always refers to a critical point. Critical point is associated with three parameters. One is critical energy, the second one is critical velocity, and the third one is critical depth. You can very easily identify a minimum energy in x-axis corresponding to the point C, and that is known as critical energy, and C has some ordinate in y-axis, and that is known as critical depth, that is yc. Now apart from any point or beyond point C, for the same energy, let's say you consider one energy E1 beyond point C, it leads to the plot of two y values, y1 and y2. So we in the later classes we call this y1 and y2 as the sequent depths, alternate depths. Now point C always corresponds to a level which is known as critical level, and the flow is known as critical flow, where Froude's number will be equals to 1, and any level or any value beyond the value of yc, let's say y2 is more than yc. If we calculate Froude's number will be always less than 1, and the flow is subcritical flow. And y1 which is less than yc will lead to a condition where Froude's number is more than 1, and the flow is called supercritical flow. And it is this specific energy curve where we can make out three separate zones: critical level, supercritical flow level, and subcritical flow level. Now in the later stage we'll try to understand how to calculate YC, how to calculate E minimum, and the procedure of quantifying the value of VC, all these three critical parameters.